Ladies and gentlemen, today we have a really exciting video because Stats Test 101. I'm going to go through all the different statistical tests that you need to know for A-level biology in respective of, whatever exam would you take. It doesn't matter. This video is for everyone. Yeah? Get a pen, paper ready, or your Google document open, because I'm going to talk at you, but everything I do say is literally to the exam, to the T. I'm not telling you anything more than what you need to know. So without further ado, let's begin. Stats tests are so neglected, literally to the last minute before the exam, because everyone's like, oh no, it's fine, I'm just going to focus on content. True, very true, but also quite a few marks actually come from stats test questions. It's actually really important you do know them. So we have a total of 6 that we're going to be talking about today. So students t-test, there's 2 versions of that. Standard deviation, Hardy-Weinberg, chi-squared, Simpson's index, and Spearman's rank correlation coefficient. Okay, let's begin. Students t-test. Basically, as I said, there are 2 versions of this. So number 1, there's paired and there's unpaired. In terms of how you calculate it, I've never seen a paired, an exam question saying, oh my god, use this formula to calculate students t-test. No, I have not seen that for paired, but I have seen it for unpaired for OCRA. In terms of what do the things mean, well, if you see X with a horizontal line above it, that's called X bar, which represents mean. Okay, so mean of A, mean of B, like group B, group A. And then you see S, so SA or SB, that's the standard deviation of group A, group B. And then N is just the number of values of the sample size. Yes, the sample size for a group A and group B, okay? So, what is the purpose of students t-test? Well, the purpose is to find out if the difference between 2 means are significant. And so for paired t-test, listen up, yeah, this is very important. If we're going to use a paired t-test, the data must come from the same individual. But if you want to use unpaired, it must come from different individuals. Now, I remember in my mock, right, there was this question, it was like, oh my god, what statistical test should the student use? I was like, gosh, easy, I see means in the question, it's going to be a t-test. And I was like, you know what, I'm a bit of a statistician. I was going to be like, oh, use an unpaired t-test. Wrong. I got the question wrong. It's because if you say the wrong version of the t-test, you actually get, they don't mark that. So it's always safe to say t-test or students t-test. Don't specify whether it's paired or unpaired in case you get it wrong. Yeah, I got traumatized after that day. I was like, I am not specifying again. Right, so, okay, degrees of freedom. You're gonna get most likely a table like this, not this extensive, but a table like this. It has degrees of freedom. You'd already calculated the t value. You need to find critical value, and then it's like, well, how do I do it, right? So how do you know when a value is significant? So you need to work out the degrees of freedom. So if you're doing a paired t-test, remember this is from the same individual. You just do the sample size minus 1. If you want to work out the degrees of freedom for unpaired, so it comes from different individuals from 2 groups, then it's just the sample size of group 1 plus group 2, add that together and take away from, so minus 2. And so everything I wrote in a yellow sticky note are the version you should memorize, and then if it's the flip, just reverse the argument, okay? So if your value of t that you have calculated is greater than or equal to the critical value that you found in the table, the difference between the 2 means is significant, and thus you can reject the null hypothesis. Let's take a step back for a second. Do you know what a null hypothesis is? Because if you don't, no worries. So, a null hypothesis is a statement that says there will be no significant difference or no correlation between things you are measuring. And the whole purpose of stats test is literally to disprove the null hypothesis, which is just it's not a H, H naught for those A-level maths kids. But how does null hypothesis like sound like? You know, what's the statement like? Well, it's a very negative statement. For example, let's say you had an experiment about light colour and plant growth, then the null hypothesis in this case would be that, oh, light colour has no effect on plant growth. So you're always saying that there will be like no effect or like no significant difference between X and Y, okay? So that is all for the t-test. And then we have standard deviation. Gosh, these examples love standard deviation. And you know what? I do too. So standard deviation is very easily calculated. It's using this formula. For people who take maths, I can't entirely remember whether if you plug in all the values into, you know, the mode and the calculator, whether you're going to get the same value as if you were to calculate it properly with the formula. I don't remember if it works. If I was you, okay, I would just go with the formula they've given. Don't do shortcuts with your calculator. Again, I might be wrong. It might work. I just don't remember if it doesn't. But anyways, I digress. So as I said, this is the formula. And so let's go through what each of them mean. So S is just standard deviation. Square root, okay, this symbol here is the sum of, okay. X represents the observation. So let's say you had, I don't know, like 39 or something, then you had 2 or something, then you had 3 or something. These would be the observations. And then X bar, as we said previously, means the mean. And then what you do is you take away the observation by the mean every time. And then after that, you square that value like this. And then after you've done that for all the observations, you add all those numbers up with after you've squared them. And then that will be your sum of X minus X bar squared. And then very easily divide all of that by the total sample size minus 1. Okay? Now, as I said, examples love this, and the stuff I wrote are to the mark scheme. So anytime you get a question about standard deviation, not gonna lie, you're probably gonna get a mark to define what standard deviation means in the first place. So it basically shows the spread of data about the mean, okay? And I've seen exam questions where it's like, oh, why do we use standard deviation instead of range? Well, this is the reason why. It's because standard deviation is less affected by anomalous results. We don't want that, do we? That's not going to be very accurate or representative to like the data we have. We don't like anomalous results. Get them away from us. So that's why we use standard deviation instead of the range. Now, standard deviation is a bit funky because you can use it to plot error bars. Error bars are shown on graphs. So you see these bars here? They are called error bars. And there's something you need to know. If your error bars overlap, there is no significant difference. So if you look over here, these bars clearly overlap. What I mean by that is, they overlap, I guess. Like, do you see this region? They're both same level. That's called overlapping. So if they are overlapping, there is no significant difference. However, if you look over here, if I was just to extend this line a little bit, you can clearly see that these two are not overlapping. So here, this difference would be significant. Okay, and that is standard deviation. Now, Hardy-Weinberg. It's in like patterns of inheritance. And essentially, we have these two formulas. You're going to be given them, really. And it's really important that you know before the exam what each letter represents. So P is the frequency of the dominant allele, Q is the frequency of recessive, P squared is just the homozygous dominant, 2PQ. Please just remember this value, yeah? 2PQ and what it represents. Heterozygous genotypes. Because, really and truly, the exam questions, if they give you like a question on Hardy-Weinberg, it'll probably be to find out the heterozygous genotype. So you best believe you need to realise that 2PQ represents that. And then we have Q squared, which is the frequency of homozygous recessive, okay? Now, the purpose of Hardy-Weinberg is like, it predicts the frequency of alleles in a population that like won't change from one generation to the next. However, This is only applied for certain like situations and conditions. That's why you're most likely going to get a follow-up question saying like, oh my god, what are the assumptions we're making with Hardy-Weinberg? Well, it's that the population must be large, that there is no random mating, there is no migration, no mutations, and no selection. Okay, literally mark scheme answers there. And there's one thing you need to know is that your values, like what you're going to be working with, what your final answer is going to be in fractions and decimals. Do not expect whole numbers, okay? Because this is probability. So for the sake of it, I decided to show a question, because it's kind of hard to say it and then not be able to apply it, you know what I mean? So here's an exam question. Okay, essentially what we need to find out is to estimate the proportion of heterozygous individuals. Remember, heterozygous represents 2pq, so that's the goal we're trying to achieve. And they've given us the equations over here. How nice of them. Right, let's start from the beginning. Capital R is dominant, and it means tongue rolling. Little r is recessive, it means that they do not allow tongue rolling. So, the total number of students who could roll their tongues is 171. The total students who could not roll their tongues is 77. As I said, you're going to be working in decimals, fractions, and must be less than 1. If you're ever in doubt, just add up these two values if you have them. That will be the denominator of a fraction, okay? Because you can't be working with whole numbers like that. At this point, I'm a big advocate for like annotating around your questions, no matter what type of question it is. So I would write that, oh my god, the first bullet point is for p squared, because that represents the frequency of homozygous dominant, okay? And then the second bullet point is q squared, which is the frequency of homozygous recessive. So after you add them together, you're going to get a total which is like 248. And now we can begin. Go with one of these values, okay? And the first equation you're going to use always is going to be p plus q equals to 1. So let's say we picked q squared, okay? Q squared would just be 77 divided by the total sample, so that's 248. Divide them, you get a decimal, 0.31. Now, we've got q squared, but as I said previously, we're going to be using this equation over here. Q and q squared are not the same, so you must square root that value, and you're going to get 0.557. Now, we can work out what q is, right? Just a simple rearrangement of the formula to get p equals to 1 minus q. So sub in the value that you got over here, which is q, and then do 1 minus that value. And then you get 0.443. Final step of the workings out is to find out what pq is. Sorry, 2pq, yeah. And that's very simple. Just do 2 times the value you got for p times by the value you got for q. And then call it a day. That's your answer, okay? So that was Hardy-Weinberg. Then we have chi-squared. Chi-squared, again, is to do with like, just like observed expected frequencies. Again, we're talking about frequencies here. So here, this like x squared thing is just chi-squared. Again, we have appearance of the symbol, which is just the sum off, okay? We have observed minus expected. After you've taken away observed and minus expected, after each like column, you then square the difference each time. And then after you've done all of that, you add them all together and divide it by the expected frequencies that was found in the table. Now the purpose of it really is to see the differences between frequencies between groups. So like an example, just to put this into context, would be like, oh, is there a difference between the frequency of different bird species at 2 different sites? Okay, and when, I'm not even going to say if, when you get a question as a follow-up with like a table like this, degrees of freedom, probability, you're going to find the critical value. There are 2 versions of how you can work out degrees of freedom. First version is based on if you just have one row or column, yeah? then it's just the number of classes, or like the number of rows minus 1. However, if you have a table of more than one row, you do the number of rows minus 1 times by the number of columns minus 1 equals the degrees of freedom. Then let's say you got, I don't know, 2, you're going to be comparing it at a probability, and then you're going to get the value, and that will be your critical value, which you use to compare with the chi-squared value you just got from the calculation, okay? Now let's link back to when is a value significant. So the value is significant when your chi-squared value is greater or equal to the critical value that you found in the table. So that would mean that there is a significant difference between the expected and observed, and therefore you can reject the null hypothesis. Okay, as I said, these arguments can reverse. So if your value of chi-squared is less than your critical value, then there is no significant difference between the expected and observed, and therefore you can accept the null hypothesis. It literally works both ways. Just memorize one. Who's got time to memorize two? No one. Then second to last, Simpson's index. This is all to do with biodiversity and like species richness and evenness. So here's a formula. We have 1 minus, okay? Oh, look at our best friend back again. The sum of n, which is the total organisms of one species, divided by the total number of all organisms, and then you square that after you've done them per row, add them all together, and that will be your sum off. And then after you've added them all together, just do 1 minus that value, and then you're going to get the Simpson's index number. So the purpose really is to measure species diversity, and again, it considers both species richness and evenness. You must realise that your answer must be between 0 and 1, okay? It's like, firstly, it's for understanding. Secondly, you can cross-check whether your answer is actually feasible or not, or like valid. So if your value is close to 1, then that means there is more diverse habitat and has a greater ability to cope with changes with the environment, okay? But then if your value is like close to 0, long day, the habitat is very, very easily destroyed and damaged by changes in the environment, making it less stable. And that's normally a follow-up question after you calculate Simpson's index, okay? Right, last but not least, Spearman's rank correlation coefficient. This one nobody really speaks about, I'll be so honest. I remember like I was in year 12 and I saw a question on it and I looked at it and I was like, so how do I do this? Like I was actually confuzzled, I was confused. It's very, very much slept on. But essentially, here is the deal. RS is just the correlation coefficient, and then we have she's back, the sum of the differences between the ranks. When I say differences, I actually mean you need to rank them. So like, let's say you wanted the highest number in your table to hold the value of 1, okay? And then depending on how many rows you have, let's say there's 10 rows, then the smallest number would have, you would write 10, okay? So you would just rank the numbers based on their order, and then you would find the difference between the ranks, okay? And then you sum them, so as in you add the differences together and times that by 6. Then you divide by the total number of pairs of the data times by n squared minus 1. And then, as always, 1 minus that whole thing. So the purpose of, Spearman's rank correlation coefficient is to rank the data in order of size. So it basically gives a numerical value to tell you the strength and the direction of the correlation. Again, for cross-checking, this is about correlation, so it can only be between the values of -1 and 1. So if your R value or RS value is like -1, that would indicate a strong negative correlation. If it is +1, then it's a strong positive correlation. And if your value is close to 0, then there is no correlation at all. And lastly, when is your value significant? So you need to compare the value that you got, so the RS value correlation coefficient, to the critical values that you would be using from the table, right? One of these tables over here. And you're most likely going to be doing it at p equals to 0.05, okay? And so, as always, if your value is greater than the critical value, the correlation is significant, and therefore you can reject the null hypothesis. Just make sure when you say that, like, oh my god, this is significant, say what it is. Like, you need to kind of be specific. So if it's Spearman's rank, you say the correlation is significant. If it is about chi-squared, say that it's the differences between the expected and the observed. If it is student's t-test, then say it's the differences between the two means, okay? That's just when you need to be a bit specific. And yeah, gosh, we did it. That's Stats Test 101. In the next video, I'm going to go through exam questions to put this into practice. I hope that was useful, and good luck on your exams. Bye!